This is a video about how a nuclear power plant works. Nuclear power plants generate electricity much the same way that most of our electricity is generated via coal or gas by heating steam turning a turbine, and that turbine turning a generator. The only difference in this one is that there is a nuclear reactor here that is generating the heat. It does not involve burning. That's one of the benefits of nuclear power, is that there is no burning, so therefore no release of the traditional pollutants that we get from burning, or CO2. So let's talk a little bit about the nuclear reaction that happens. So the uranium fuel is a large atom, and large atoms that have very big nuclei tend to be unstable, lots of neutrons in there. And so when a neutron leaves uranium, which is just kind of happens spontaneously, that neutron's got a lot of energy in it, and it could hit one of these, a neutron from another uranium could hit this uranium atom. And when it does that, with its energy, it can break it apart into two different atoms. That's breaking apart one nucleus into two nuclei, two smaller nuclei. And this is called a fission reaction. Not only does this fission reaction create two different nuclei, it also emits a few more neutrons. Now, a lot of times those neutrons in nature would just get absorbed by whatever's in there, other atoms. But if there's a high concentration of uranium-235, which is unstable, those neutrons themselves might hit other uranium-235s, and a chain reaction occurs. If this chain reaction occurs, then an incredible amount of heat is produced. If it continues, it could end up being an atomic explosion, like in atomic bombs. But we need to regulate that so that doesn't keep going on. That is a fission reaction. It releases a lot of heat. So how do you slow it down? Well, what creates a reaction in the first place is those neutrons that are hitting the uranium-235 nuclei. So what we need to do is we have these fuel rods. This is where the concentrated uranium-235 is. And we have control rods. And these control rods absorb neutrons. So if you put these control rods in between the fuel rods, they'll absorb the neutrons, and hence the reaction can be kind of controlled that way. And that's important, because what can happen is if something goes wrong, and this does happen at least 3 times with Chernobyl, 3 Mile Island, and then recently at Fukushima power plant in Japan, there can be what's called a meltdown. That's when the reactor gets so hot, something happens, either the fuel rods are not put down in time, it runs out of cooling water, and then you get what is called a meltdown. That's when the reactor gets so hot that it physically melts, and then there's nothing you can do to stop the reaction, because at that point fuel rods aren't useful. This containment dome will protect against all of the radiation that gets released. The problem is that during a meltdown, hot steam, if there's lots of water in here, will be created. This will create so much pressure, it could explode the containment dome, so they have to release the steam, and then that steam is radioactive. One thing that you can see here is that normally, under normal conditions, the steam and the water that cools this reactor never leaves the containment dome. That water then heats other water that then leaves, and that's a protection. But if there's something wrong with this steam here, it gets released. That's when it's a problem during a meltdown. So an uncontrolled reaction can't be stopped, and it melts. One of the big problems with nuclear power is storing the waste. You end up with these daughter nuclei like we saw, strontium, barium, and these are radioactive in themselves. So after a while, the fuel itself isn't very usable, and that's got to get stored. And it's radioactive for hundreds of thousands of years. So what do we do with this waste? Because we can't put it in a container that's going to last long enough. So best thing to do is to store it underground, And there is a plan for that in Nevada underneath Yucca Mountain. So here we have these long tunnels, and then we have this repository down here well underneath the mountain. But there's some problems with this. First one is no one wants it in their backyard. So these plans are actually on hold. And so we really don't have any plan to store nuclear waste. But even if we did, how would we've got to label it in such that people, even 100,000 years ago from now, would know what it was. So what do we do presently? Well, presently, since we have no repository for it, all the nuclear waste is actually stored on site. So we have a couple places where that happens. This is the low-level radioactive waste. It could be probably not spent fuel rods, but maybe water that needs to be stored. And then over here, we have the storage of the spent fuel rods. It's crazy to have them stored all over the country, wherever there's a nuclear power plant. Lots of consequences, though. If we were going to store it someplace else, how would we get these fuels, these spent fuels, to, say, Nevada? We'd have to send it in trains and trucks. And so this is our best possibility right now, is just keep them on site. So we need to understand how to calculate the half-life. That's the problem that they might ask you on the AP exam. And a half-life basically means the time it takes for half of the parent material to decay into daughter material. So if you start with uranium-232, it decays into thorium-228. That just happens naturally. And so the question would be, well, how long does that take, right? Well, the half-life of uranium-232 is 70 years, which means after 70 years, half of the 232 will have randomly sort of just decayed into thorium-228. How much? Half. If you have 1 gram, then half of it will have randomly changed in 70 years. If you had 1,000 grams, well, then 500 grams would have changed after 70 years. So if you started with 100 grams, we can try to figure out how much is left after 1 half-life, which was 70 years for this parent material, or after 140 years, or after 210 years. So if you have 100 grams, well, how much would be left after 70 years? Right? 50 grams. That's half. What about after 140 years? Well, that's 70 years from the 70-year mark. So what's half of 50 would be 25 grams, or half of a half, which means about a quarter would be left. And what about after 210 years? Well, after 210 years, that's just 70 more years, right? So if you started with 25 grams, half of 25 is, sorry about that, 12.5 grams, which is a half of a quarter, right? If this one was a quarter, and then the next would be a half of that, so that would be an eighth. So that's how you calculate half-life. If you got questions on how to do that, I'd be happy to explain that again during my office hours. And that's it for nuclear energy for now.